Hi, good day to you all. I am very happy to be here at the 5th International Workshop, HAAPIE 2020, held in conjunction with ACM UMAP 2020. I want to thank the organizer firstly for accepting our paper and secondly for the prompt and efficient response in adapting to the current worldwide circumstances. My name is Sergio Ramírez. I am a PhD student in the civil laboratory in the University of Lille in the north of France since last December. My thesis directors are Ms. Nour and Mawas and Mr. Heutte. The civil laboratory research fields revolve around pedagogical work, didactics, and adult training, most precisely within the context of lifelong learning. Within my doctoral research work, I found myself facing the need to discuss the learning model subject. So today I'm happy to present to you the result of this discussion, approaching the paper towards open learning models, including the flow state. The presentation is divided into three parts. I will begin with a brief situational and introductory part, where I will also present the motivation and aim behind this paper. Then I'll proceed with the presentation of our open learning model proposal, the heart of this paper. And I will finally conclude with the perspectives of this work. As non-formal, informal, or incidental learning represent the vast majority of adult learning, access to and effective use of relevant information and continuous learning in MOOCs, among other things, are essential for lifelong learning, or LLL. This refers to the idea that learning should occur through a person's lifetime, involving formal and informal domains. Yet, MOOC abandonment rate is very high, around 93.5%, while we have known for a while that engagement, intention, and motivation are among the top factors to affect performance in MOOCs. Research has shown that content and path personalization can have a positive effect to decrease MOOC abandonment rate. At the same time, learners' personalization is one of the essential concepts that come back in a positive view while studying LLL. However, while modeling the learner's knowledge in MOOC is a common practice, or its distorted view, misconception, or even forgetfulness, modeling the learner's psychological state is an often relegated concern within the community. This is while characteristics such as learning environment, learning styles, learning preference, etc., are an addressed concern within the modeling community, very few consider the learner's mood or the psychological state as a relevant, measurable, and active aspect to take into account while designing a learning model. This represents a serious setback for the learner, as the learner's psychological state carries a preponderant weight on the learning process. This motivates us to propose an open learning model that, besides knowledge, also accounts for one of the learner's psychological state in the context of digital environment for human learning. That would be the optimal experience, also known as flow state or the autotelic experience. That is to say, how to model in order to detect this learning optimal experience in digital environments. So in order to achieve this goal, we propose a technical and functional architectures that best suit the modeling of the psychological experience, additional to the knowledge modeling. I imagine you may be having a few questions, of which the first one, what is flow? Well, the flow state is a phenomenon that explains why people perform activities for the sake of the activity itself, without extrinsic rewards. This flow experience is triggered by a balance between a person's skill in an activity and the challenges afforded by the lifelong learning environment. It is also known as being in the zone, the autotelic experience, or the optimal experience. Flow state has been shown to promote learning and personal development because deep and total concentration experiences are intrinsically rewarding, and they motivate the students to repeat any given activity at progressively higher challenging levels. In this study context, this flow experience is triggered by a balance between a person's skill in a learning activity and the challenges afforded by the LLM environment. Another one of the questions you may be, why flow? Why to model flow? If there are more psychological states, of course, such as shame, reproach, distress, joy, pride, admiration, and for some authors, motivation and engagement. Well, mostly because flow correlates learning favorable metrics that englobe a few of these states, like motivation, self-efficacy, self-regulation, goal attainment. Also, Some of these metrics are central, accounted for dimensions on solid learning models. Studies show that it is crucial, if we are to provide customization in any e-learning system, to store not only the learner's characteristics, the static and the dynamic personal information, such as skills, knowledge, environment, goals, etc., inside the open learning model, but also to consider as faithfully as possible the learner's psychological state, preferences, and reasoning process to promote positive emotions that foster learning. And for that matter, EduFlow 2, the psychometric tool we use, is a proven, research-tried measuring mechanism to accurately determine flow in educational and online contexts. In this paper, we are interested in open learning models that I'm going to call for now OLM, and not only learning models, which I call LMs. We aim to propose a model that allows communicating its content to the learner or to any other actor through visualization and editing to be a step forward in the use and design of predictive learning models by allowing us to have an insight into the nature of the dialogical interactions and learning. Our proposal aims as well to improve the accuracy of the learning model, to effectively represent the dynamic nature of the learner states, and to support the learner's metacognitive process of reflection. As to the flow learning proposal. This paper is based and extends the work of Mawas et al. 2018. So every time I refer to the original paper, I refer to this one that you see on the screen. In it, its authors propose a functional and technical architecture in MOOCs within a lifelong learning perspective. This original paper, along with 4 others, were recently highlighted in a literature review as the most suitable open learning models for MOOCs in a lifelong learning perspective. The functional architecture. Complementary to the original paper we take inspiration from, we envision 4 main roles instead of 3: the pedagogical engineer, the teacher, the learner, and the psychological researcher. Here, I quickly review its newly functional architecture. The learning map, LMAP, editor is a replacement for a typical linear course description where content is static. It is used by the pedagogical engineer to upload the course content and structure as one entity, as the course structure is part of the domain model, DM. It is also used jointly by the psychological researcher and the teacher to define the flow model, FM, that is the flow instrument, and the jointly agreed situations in the course structure were applied. This way, the learner gets personalized content through a course navigation plugin according to the learner's own open learning model, to the domain model, and to the newly implemented proposed flow model. So this way, both teacher and learner have access to the OLM through the dashboard, the OLM dashboard, where they can visualize the learner's progress and negotiate a modification if it's needed. To the technical architecture. Also, the original paper technical architecture relies on 3 main components: the MOOC environment, the learning record store, LRS, and the LMAP core. Now, to accommodate the learner's flow state in the open learning model, we propose to extend the LMAP core with a flow models database that we see in white, bidirectionally linked to a flow model interface, also in white, and unidirectionally feeding the existing selector. Our additions then from the original paper are shown here, highlighted in white. So this way, data is collected from the different learning services and platforms via HAAPIE 3, and it's transferred to the LMAP core via the LRS, we can see here. So it is the LMAP core's task to store and to update the DM, FM, and the OLM. Inside the LMAP core, the Learning Model Updater, the LMU, updates the open learning model based on data collected by LRS. The selector chooses personalized content from the DM and the newly added FM, according to the current open learning model state, communicating to the course navigation module, data accounting for the learner's flow state, and this way then providing the learner with a personalized flow state accounted access. Access to the models is provided separately by the DM interface, the OLM interface, and the newly added FM interface, which are at the top. Akin to the original proposal, the OLM interface enables achievement updates and access. The interactions with the learner and the teacher are done through the OLM dashboard in the MOOC. The DM interface enables domain models creation, modification, and deletion, as well as the flow model interface enables the same actions to the flow models. Both the FM and the DM interfaces are defined for the DM editor within the MOOC. Now, I will present in detail the domain model, the flow model, and the open learner model of proposal. The original domain model comprises three main layers on which sets of interconnected and related nodes representing hierarchically subjects SR, topics TN, and concepts CP will instantiate for any given knowledge. We reprise this model without changes. As an example of this model once instantiated, the subject could be, for example, a course of Java, C# or Python, where topics could be, for instance, inheritance, variables, functions, constant topics, while their inner concepts would lay in the appropriate bottom layer. Well, notice that a given subject can be composed of many topics and hence of their accompanying concepts. This model could be imagined as a corresponding image to the teacher's course plan on any subject. As such, the domain model is prepared by the teacher, who is the domain expert in our case, and the learner does not intervene in the design we present here. Now, our flow model proposal relies on the EduFlow2 psychometric instrument to measure it. This instrument is a 12-item scale purposefully designed with educational scenarios in mind, created by Mr. Heutte in close collaboration with Mr. Csikszentmihalyi, the original mind behind Flow. It differentiates 4 flow dimensions from D1 to flow D4, with 3 items per dimension, A, B, or C. Flow D1 then corresponds to cognitive control, flow D2 to immersion and time transformation, flow D3 to loss of self-consciousness, and flow D4 to autotelic experience. So, the flow model relies on the domain model and on the current state of the learner model. That means there is one flow model for each subject SR in the learner model. As such, the flow model, which we see here, has no node on the subject layer. Hence, the EduFlow2 instrument sits on the topic layer with its 4 composing dimensions D1, D2, D3, and D4, and their inner relationships laying on the concept flow layer part, as we see here. Now, the open learning model, originally seen by their creators. The OLM, based on the generic Bayesian student model GBSM, is composed of knowledge and evidential type variable nodes in a 4-layer structure. On one hand, knowledge variable nodes Kn represent the student's knowledge in any form or type, with their values not being directly observable. Knowledge variables correspond to nodes sitting on any of the 3 layers of the DM. On the other hand, evidential variables Qn, representing students' actions, are directly observable, and they correspond to, for example, the result of a knowledge exam. That means that the learner dimension exists through these questions, through their questions in general. Notice the change of arrow's direction between concepts and their evidential variables. This is because concepts can be evaluated through many questions of exams or instruments. The evidential variables values will be used to calculate the values of the hidden knowledge variables. In the GBSM, knowledge and evidential variables are binary, with possible values of 0 and 1, which represent unknown, incorrect, or known, correct. Evidential nodes sit on the evaluation layer and are linked to relationships. So it's important to note that aggregation relationships will occur between knowledge nodes, between concepts and topics and subjects, whereas causal relationships will link knowledge to evidential nodes, so key to Q. The model holds Then the learner's knowledge. The questions and the model design come from the teacher, which is in our case the domain expert. Because knowledge can vary in time, this model dynamically represents updated learner's knowledge. Well, here is the flow model showcasing the EduFlow2 tool instantiated. Here we show the FM as an instance of the EduFlow2 instrument results. The results of the psychometric tools designed to detect the flow state, the questions from Q1 to Q11, I already presented you, are on the evaluation layer, but because they are evidential variables and are causally linked to the flow variable nodes, FD1 to FD4, in the concept layer. These evidential variables correspond to the learner's results to the 12-item scale in the EduFlow2 instrument presented previously. This model holds the learner's flow state per subject. The questions and their design come from the psychological researcher, while the application moments are agreed jointly with the teacher. Here, the OLM is represented containing subject S1 to SR, as we already saw, along with its N topic nodes, P concept nodes, and Q evaluation nodes. As the flow state depends on the subject SR and on the OLM state, there will be as many FMs as there are subjects from S1 to SR within the OLM. This is to say that for every subject SR, there will be one FM. This corresponds then to the FM for the subject S1. This is the FM flow model for the subject S2, and so on. This, the last one, is the FM for the subject SR of the open learner model. Moreover, as the OLM is automatically and dynamically updated to reflect learner's knowledge on the left side, its corresponding flow model, FM, must be updated as well in the center. However, this update of the flow model is not done in real time, as it requires human intervention. That is, the learner actively answering the EduFlow2 instrument at preset course moments, which were previously determined by the teacher and the psychology researcher jointly. The dynamic nature of the OLM implies that there will be as many instances of FM flow model as there are predetermined moments to apply the EduFlow2 instrument in the course for all and every subject SR. This is for any instantiation SR of the OLM. One corresponding instantiation of the FM also exists at that specific moment in time. This allows for accurate knowledge and flow representation in a lifelong learning context. This is an instantiation of S1. This is an instantiation of S2 for moment T. This is an instantiation of this of S1 for moment T plus 2. T plus 1, T plus 2, T plus 3, T plus 1. So you can imagine that the flow model gets created as a matrix of R rows and N X columns. Well, this leads me to the conclusions and perspectives of this study. So this study approaches the issue of including the flow state in OLM from MOOCs in an LLM context. It addresses how to model the flow state, what instrument to use to represent it in the OLM, and what technical and functional mechanisms to consider in order to access, update, store, visualize, and edit the flow model to be used for learners' content personalization. It does so by extending and proposing a functional and technical architecture that accounts for the flow psychological state, comprising a domain model, a flow model, and an open learner. The perspectives future work will aim to, in the short term, to evaluate the accuracy of a proposal, first on an ad hoc created MOOC hosted by the University of Lille about basic Python programming, and second on a French-spoken international MOOC about project management. In the midterm, further research is planned to include additional instruments that measure the flow state to improve the accuracy of the model, as well as envisioning to incorporate digital traces like system logs as evidential variables to set course to an automatic trace-based flow modeling. Thank you all for your attention. I am now ready to answer your questions, if the connection allows it.